Okay, so some issues that I want to talk about. We want to talk about phase in circuits. We're talking about circuits. If you just have a simple voltage source with a resistor, a load resistor of some sort, the voltage produced, and let's take this out. I want to put in a varying voltage, an AC voltage. As the voltage source increases, the voltage across the resistor increases, right? Here's the voltage source, V sub V, the voltage at the voltage source. And it's going to continue like that. The voltage across the resistor is identical. That's referred to as in phase. So they are perfectly in phase with each other. If I have a voltage source going across a capacitor, yep, assuming the same voltage pattern, the voltage across the capacitor is going to charge. So the voltage is going to start, well, it'll start building voltage whenever it's positive, but it'll be building the fastest when it's at its highest point. So this is where it's going to be at the peak of the curve, right here. So it's going to look something like this. It's going to reach its peak where this is 0. Then when it's negative, it's going to start coming down. It's going to reach its biggest negative when that's 0. So it's going to look something like that. Yes, it's going to be 90 degrees, call it negative 90 degrees out of phase. Yep. So the capacitor, the voltage across the capacitor is literally 90 degrees behind, or a quarter of a cycle behind the voltage. If you have an inductor, it's the current that lags in an inductor, right? So we do have to have a voltage there. But what happens in an inductor is the inductor will be at peak voltage. I should use L for inductor. It'll be at a peak voltage when the voltage is at 0, and as the voltage increases, the inductor actually loses voltage. So it's going to look like this. So an inductor is actually 90 degrees, positive 90 degrees out of phase. I got that backwards. This should be positive, and this one should be considered negative. A lag is a positive voltage. So whether we're talking about voltage, current, or impedance, capacitors and inductors don't have resistance, but they do have impedance. It's still measured in ohms. Your phase diagram should probably include the A in there. Your voltage across the resistor, voltage or current across the resistor is at 0 degrees. The capacitor, voltage or current across the capacitor is 90 degrees afterwards. The voltage across an inductor is 90 degrees before. So it's 90 degrees ahead of the resistance. And of course, there's nothing over here. So let's say you have in a question like 2627. Now this is not question 2627. I'll just warn you that. This is similar to 2627. Let's say the current, so the current has the same phases. Current through the resistor, current through the capacitor, current through the inductor. Now, it's not necessarily current through the capacitor, it's current through the resistor that's next to the capacitor, and current through the resistor that's next to the inductor. So anyway, let's say I tell you that the current through a resistor is, what do I want to do? Let's say it is 60 milliamps. The current through an inductor is at, let's just go 11 milliamps. I want to find the magnitude and phase angle of that resultant current. Not necessarily. What you have here is you got the current through the resistor is going to be this way, 60 milliamps. Right? Current through the inductor is going to be this way, 11 milliamps. Oops, wrong way. Inductor goes down, doesn't it? So the inductor will be this way, 11 milliamps. I want to find, did I do that backwards? Yeah. Current flips. Current through a capacitor trails. The voltage through a capacitor trails, but the current through a capacitor leads. So it's going to be like that. So this should be 90. So it's 11 milliamps that way. So to find your resultant angle, we've got to add those two together. And what we do is we just slide this one over here like that. There's a right angle. You're looking for that length and that angle. So if this is 11 and this is 60, how do I find that length? You got it. 60 squared plus 11 squared, right? Gives you 61 milliamps. I believe. And how do we find this angle? We have the opposite side and the adjacent side, right? So we're dealing with a tangent. So it's an inverse tangent of opposite over adjacent, 11 over 60. Does that make any sense?
I had it right one of the times I did it.
So 10.39 degrees. So yeah, that would be, IT would be 61 milliamps and theta would be 61.93. Obviously your numbers are different. So I'm going to pause it here for just a second, let you guys do that properly. Okay. Now 28 and 29, looking at ones like this. We're looking at a function, a trig function basically. Your instantaneous voltage is equal to, I'm going to put INST for instantaneous, or VINST, is equal to your peak voltage times the sine of 2 pi ft, where f is your frequency. What frequency does power run at?
I just realized I completely knew how to do that. I just didn't know
Yeah.
how to do it last night. I kept on thinking it was feet.
Oh, nope, frequency. So frequency is going to be 60 hertz. So frequency, F is always going to be 60. T, this is the tricky part, T is time in seconds. What happens is this here gives you an angle in radians. So you have to do one of two things. Either it has to be divided by, well, was it 2 pi equals 180? So you either have to convert it into degrees, or you have to leave it as radians and change your calculator to radian mode. So I'm going to change my calculator to radian mode. I'm going to hit mode, and I'm going to go down to where it says radians and degrees. Right now it's in degrees. I'm turning it to radians. Your calculators will have a similar thing. Should be in a DRG key somewhere, I believe. And it changes it to from nothing to rad. It should now say across the top of the screen somewhere. Yours is a little bit different, Andrew. I'd have to look at yours. Do you know where to do it? Or convert it? Okay. If you were going to convert it, you know that 2 pi radians equals 180 degrees. So you get 2 pi ft times 180 over 2 pi. The 2 pi's cancel out. It's 180 ft. So that would go in here. Instead of 2 pi, it'd be 180. Sorry, not 180. This should be 360, shouldn't it? 360 equals 2 pi radians. So this would be 360 ft. So 360. No, a radian, 2 pi radians is a full circle. Pi over 2 radians is a quarter of a circle. Pi radians is half a circle. So would you rather do it in degrees? Okay. So I'm going to turn this back to degrees. Let's clear it out. So the formula we're going to use is the instantaneous voltage is equal to the peak voltage times sine of 360 times the frequency times the time. So what is the instantaneous voltage at time equals 8 seconds? Yes, at any whole seconds it should be 0. Let's test it out. So we got 170 volts times the sine of 360 times 60 times 8. So 170 times sine. This will sometimes give us something weird like 10 to the negative 9th or something like that. This does give us exactly 0. So there we are. So 0 volts. Yep, that's it. What's the instantaneous voltage? It is 0 volts. At any whole second, it would be 0 volts. So then, what is the time, the first time after t equals 0, so after 0 seconds, that the instantaneous voltage is 120. So we're going to put 120 here, equals 170 times the sine of 360 times 60 times t. We've got to solve this. How would we solve this for t? Well, I'm going to do this. I want to say what's the first time. I'm going to change this a little bit, so I'm not giving you the answer. Let's do what's the first time that the voltage equals 60 volts. So I'll put 60 in there instead of 120. Obviously, you're going to do the same process with just 120. You're going to divide by the 170. So now I'm going to keep this in my calculator. 60 divided by 170. I'm going to write down the decimal. Oops. Let me try that again. 0.353, but I'm keeping it in my calculator, equals the sine of 360 times 60 times t. I could have done the 360 times 60, I just didn't for some reason. That is what? 21,600, I believe. So now we have to do the inverse sine to get rid of the sine. So I'm going to do second sine, second answer, yes, to inverse sine that answer, so I don't have to punch it back in. So I'm at 20.67. Yeah, so now I'm going to divide by the 360 times 60, which is 21,600, right? So I'm going to divide by 21,600. So I get, now that's scientific notation, 9.568 E negative 4. What does that mean? What that's saying is 9.568 times 10 to the negative 4th. So what does that mean? I moved the decimal point 4 spots to the left. So that's 0.0009568, which would be 0.957 milliseconds, or 957 milliseconds, or 957 microseconds. One of the two.
So I think I'm on the got the answer with all around
here. Yep. What did you end up at? For the actual 120 volts.
Yeah, for that one, last time I ended up at 2.9 something milliseconds.
That's a little too far off.
But see, the thing is, the way I did it was basically a whole lot of leaps and logic.
Okay. It should be just over 2 milliseconds.
Yeah, it's 2.07.
Perfect. Any questions? Okay, number 30. I'm going to give you one like number 30. This goes off of that whole phase diagram thing again. Here's my resistance voltage. This is my capacitive voltage. This is my inductive voltage. I am told, I'm going to give you different numbers. So let's say we have a total voltage of 250 millivolts. I am told I have a voltage across a capacitor of 90 millivolts. Voltage across a resistor of, let's go with 240 millivolts. Find voltage across the inductor. Given that the voltage across the inductor is greater than the voltage across the capacitor. Why did I need to know that? Well, there are two possibilities here. I've got that voltage across the resistor is 240. So that's 240 millivolts there, right? The voltage across the capacitor is 90. We have a total voltage of 250 millivolts. Well, depending on what the voltage across the inductor is here, that 250 millivolts could be right here somewhere, or it could be right here somewhere. Does that make sense? Without this knowledge, I don't know which one it is. If I know that the voltage across the inductor is bigger than the voltage across the capacitor, what does that mean as far as the vertical component here? It's got to be, this one's got to be bigger, right? So if this one's bigger, that means it goes up top. So that means we're looking at this one up here, not this one. Oh yeah, it's going to be a right triangle because we need this component. What we're looking for is this piece here. If this hypotenuse is 250 millivolts and this piece is 240 millivolts, what does this piece have to be? So you do a squared versus b squared equals c squared. This would come out to be 70 millivolts. Does that make sense? Again, your numbers are different. For that to come out to be 70 millivolts, this has to be 160 millivolts because the 90 here cancels out the 160 to make it 70 because they're opposite phase. That makes sense? Yeah. That's how you find the total voltage of a circuit if it's an RLC. Works with those phases. That's how they add up. The voltage across the inductor works against. It cancels out voltage across the capacitor.
Okay. I don't think we ever actually did
the phase.
The actual formulas that add
Oh, sure.
voltage, but I remember the phase stuff.
Oh, sure.
One follows the other at this angle, and the other one at this angle.
Okay. Well, let's say I give you that the total voltage is 250 milliamps, or millivolts, I should say. Voltage across the resistor is 150 millivolts. Voltage across the inductor is 90 millivolts. Find the voltage across the capacitor. Now you might be wondering, well, don't I have to tell you which one's bigger, the inductor or the capacitor? Well, you might. Let's take a look. So this is 150 here, that's VR. VL is 90. I'm dropping the millivolts just to make the geometry work. If the total here is 250, so there's two possibilities, here and here. So either this is 250, this is 250. What would this length have to be in either side, in either state? Well, this would be a right angle. Square root of 250 squared minus the 150 squared is 200. Is it possible for it to be this one up here? No, this only goes 90. So it can't possibly go 200 up, right? So it has to go down 200. So this one can't happen. So that means we have to have 290 has to be your, come on, 290 millivolts has to be our VC. So it can go down a net of 200. Does that make sense? Okay. I'll let you guys finish up number 30. Any other questions off the test you have any questions on?
I just want to, is number 30 is the answer to number 30, 103 millivolts around there?
A little bit bigger than that, just a touch.
Yeah, and then close, but I don't know what I'm doing.
I'm going to give you this. This is 120 here.
That was what I did last time.
Oh, gotcha.
Not just now.
Okay, I'll make you start
Now
over.
I can figure it out, but-
I'll make you start over on it then. Yes, do that problem and turn in your test and I'll let you guys out of here.